Math is so easy. It's just math. Lesson 4, pulling a rabbit out of a hat. I hope that was a cool lab for you. We're going to look at the ready, a little bit of the set, a little bit of the go. Hope you're having a great day. What are we doing? We're using the product rule or quotient rule to write the expression. Recall, product rule. These are two bases that are the same. Whatever their exponents just happen to be. Let's say that this is b and an exponent of c. We can just add those on up. Key thing is that the exponents have to be the same. Super big. Please don't forget that. And I guess the quotient rule, if you have, let's say, a to the negative x exponent, whatever x is, let's imagine it's some number, and this is all negative, you can rewrite this as 1 over a to the x power, where notice this is a positive exponent. That's your brief refresher on that. Let's look. We have the same bases, so just add up those exponents. 6 plus 5 gets you 11. Feel free to rewrite that, or don't, because you just need to rewrite it with positive exponents. We can take this here. Negative 4 plus 7 is going to get you 10 to the third. It's good as is. Feel free to leave it like that. Let's do this one. This one looks kind of cool. All the same exponents, or the same bases. So throw that all together. 6 minus 3 plus 1. So 2 to the fourth. Capiche? And I guess this is a form that you might see the exponent rule, where you can take whatever your top exponent is, subtract your bottom. So you can take 5, deduct 2. This is going to get you 7 to the third. And if you're not convinced that this works the way that it does, imagine if you just kept writing out all of those 7s, like so. Wouldn't you be able to cancel 2 of these jabronis? Look what you made me did. I wrote 2. I needed to write 7. You can cancel that, cancel that. Notice you're left with 7 to the third. There you go. Super simple. You can do the same with these other ones, and this might be an interesting one to do. So even though these are both negative exponents, you can still think of it as your top exponent, subtracting your bottom exponent. Negative 4 minus negative 8 is pretty much negative 4 plus 8, which is, in so many words, 7 to the fourth. And you can do this here too. P to the negative 3. You're getting rid of 5. So this actually just goes more negative. It's p to the negative 8. Aren't you glad I showed you that quotient rule at the beginning with that fraction? So you can rewrite this as 1 over p to the 8. There you go. No negative exponents here today. I'll see you in the set. Let's start simple. We'll do 16. F of 16, given that f of x is this. And maybe I'll color coordinate here. I hope you don't mind. I'll probably switch back colors at some point, but I'll do my best to kind of color coordinate that we're dealing with 2 different equations here. So 2 different equations. G of x is x squared plus 7. F of x is square root of x minus 1 after you took the square root. So let's do g of 3, because I'm already writing like this. Instead of x, putting in 3, square it, and add 7. 9 plus 7 is 16. And I guess they want us to also do f of 16, which is fine. I'll color coordinate here. I can do that. Where this is square root of 16 minus 1. Square root of 16, you know that's 4. Get rid of 1. That's 3. There you go. What are they also going to ask us here? Let's look. What do your ordered pairs for f of 16 and g of 13 imply? I mean, the outputs are the inputs of the other. I mean, we know that this output was 3 and g of 3 was 16. Do you see how these kind of switched around? So what do the ordered pairs imply? That the output for f of 16 was equal to the input for g of 3. Does that make sense? Do you notice that little bit by bit? Follow the arrows? That makes sense to me. F of 25, we're taking the square root of 25, we're deducting 1. Pretty simple. Minus 1, so this is 5 minus 1, so this is 4. Based on your answer for f of 25, predict g of 4. It's probably going to be 25 because we saw that little switch. Find g of 4. Did your answer match your prediction? I'll leave that up to you. And also leave f up to you too. So hopefully as you worked through the set in 1.4, you were finding all of the inverses, meaning you were putting in the work, and it probably started off with something like switch x and y, and then solve for y, something like that. Kind of do the same thing here. So we have 3x plus 5. And if I switch this around, it's now x equals 3y plus 5. So solve for y. So get rid of 5 on both sides. This equals 3y. Divide by 3. So now we're looking for a function that's x minus 5 divided by 3. And lo and behold, boom, it's right there. So 3. So that's done. You can do the same song and dance for b. You can say that this is going to be x equals y to the 5th. How do you think you can get rid of this exponent of 5? Hopefully you're saying by taking a 5th root. Do that here, do that here. So your inverse for this is going to be the 5th root of x. Do we see something like that? We do. There it is. Oop, there it is. There we go. These are, the logs, hopefully you dealt with that. Maybe we'll see one of those. Let's do that. So let's say this is y equals 3 to the y. We're solving for y based off of logs. We can take this, throw it back as a base, and then just write log before it so that it's log base 3 of x, and it equals y. Think of it as just an interesting way to write exponents. That's how logs are going to be. I don't know if we'll see them a ton in this section, but definitely in future ones. And for what it's worth, this is 5. Capiche? Sound okay? Follow those tips. You'll be doing just fine. These are fun. All right, composite functions. We have f of x as something, g of x as something. We're taking one, putting it into the other. Let's do 15 first. So what are we doing with this? F of g of x. That's cool. It's nice. It's lovely. But I want to challenge you to get into the habit of rewriting what your input is. So if g of x claims to be x minus 5 over 2, write that because it's really going to help. And then you can fall back on what the rest of that equation looks like. So instead of 2x plus 5, leave a little bit of a blank and write in what your new input is. And then just evaluate that. So you're taking two versions of this fraction, so that cancels. You're now left with up top, x minus 5 plus 5. Your 5's cancel, so this equals x. So that's f of g of x. And I guess this is trying to build up the idea that these are functions that you're working with. So a good rule of thumb is that if you were to impose or use composite functions where one's the input and then you change it and make it like the outer function, then that's hopefully going to give you an output of x. That's how you can know that those are inverses. So maybe that's something to share. And the fact that this all boiled down to x means that they're inverse functions. These two should be inverse functions. Hopefully we see that on the same outcome. So let's now do g of f of x. Again, keeping g on the outside round the outside. Throw in what f of x is. It's 2x plus 5. And just throw it in for x. X is right here. So let's, instead of x, put some space, put parentheses, put 2x plus 5. We then deduct 5. So that's here and here. And all that's dividing by 2. So let's simplify some of this. And don't be afraid to rewrite it a bunch if you have to, but at some point, challenge yourself to not have to write parentheses. Maybe notice something is going to cancel. So your 5s cancel. This is an L over 2, but it's just 2x over 2. So your 2's can cancel. So lo and behold, it's equals x. Simple, right? You'll probably do the same thing for all of these other 16, 17, 18. So do that similar kind of setup. We'll skip 19. But again, if you have questions on these, let me know. Well, maybe we'll do one. What's this asking? Match each graph with the correct pair of functions from there to there. Label f of x and g of x, and graph the line y equals x on each of the graphs. The graph matches functions from number blank. Graph the line y equals x on the graph. I mean, they should have kind of did this, but we'll sketch it out real quick. All right, so I know what they need to do. They're saying based off of these bits up here, match it with a graph. That's what they're trying to do. So what can we say? We can say that maybe we'll do the simple ones. Let's go with simplicity. Let's look back at 15. 15 had a linear function. 17 had a linear function. So maybe we'll hunt those down and narrow it down that way. So let's find one where it's 2x plus 5. That's not it. That's not it. Okay. So this one, 2x plus 5. Simple enough. Because it starts at 5. It goes over 1 up 2. So this could match what you saw in problem 15. So it's f of x for this. So this is 15. And this also is going to keep pushing you to graph y equals x. So feel free to do that. They're trying to hit home the idea that if they're inverses, they reflect over this line. So don't get lazy with that. Give it a shot. You're so capable. And this should be x minus 5 over 2. Okay, capiche? Which, if you really think about it, is just going to be 1/2 x minus 5 halves. Which, ballparked, yeah, it's kind of what's happening. Keeps going over 2, up 1. So that's what you'll do with the other ones. Kind of match it out. Recall the other one was linear. So that's going to be 17 right here for this other linear one. So this is from 17. Feel free to graph out that function as well. And I'll leave the other ones up to you. What else do we have? I mean, I think we kind of hit a lot here. The Go has quite a bit. It's trying to hit the idea that, yeah, you can take inverse functions and also graph them out. So don't be afraid to do that. If you have any questions, let me know. Reach out. Thanks for watching.